Alright, so in the previous video I talked about what differential equations are, and in this one I'm going to show you a few examples with first order differential equations and a technique called separation of variables. So the first technique you usually need to learn when solving differential equations is that of separation of variables, and what that is that if you're given a differential equation of the form y dash equals f x y, so this is just shorthand notation for dy dx, and it could be any function of x and y. And what this means is that on this right hand side you can have any functions of y as well. So you can have something like, say, x squared plus y squared, and you're solving for the function y. So that's a valid first order differential equation. Now, separation of variables consists of something very simple. What you need to do is you're gonna integrate both sides. So you're gonna take dy dx and integrate it with respect to dx so that this differential basically cancels out, and you're gonna integrate f x of y. Now the important condition for this to give you a useful solution is that you need to have a particular function in which you can actually separate the y from the x. So in this particular example here, you cannot do that because there's no way for you to separate these two without having to act specifically on y with the integral. So what would be an example of a separable differential equation? Well, it would be something like this. Let's say you have dy over dx, and you have something like x y times y minus 1. Now, is this a separable differential equation? Well, yes it is, because you can take the fact that this is a product of two functions. This is a function of x, and this whole section is a function of y. So if you divide both sides by y times y minus 1, so I'm just going to write the integral directly like that, and then x dx. So what you're going to be doing here is you're going to be integrating this function, so with respect to y, and this function with respect to x. And then once you have that, whatever expression you get here, you're just going to rearrange the terms such that you get an explicit expression for y in terms of x only. So I'm going to show you a very simple example here with a first order differential equation. So suppose you're given the equation dy over dx equals 3y. Well, this one is very simple. All you need to do is you move the y to the other side, and you're going to integrate both sides. So you're going to have integral of dy over y equals to integral of 3 with respect to x. So let's integrate these two. We know right off the bat, we know that this is going to be the natural log of y, and well, it should be positive there, and this is going to be just 3x plus some constant c. Alright, that's straightforward enough. So how can we make this into an expression for y that is explicit? Well, we can just take the exponential of both sides to get rid of that natural log, and then we're going to end up with e to the 3x plus c. And by the laws of exponentials, we can actually combine the powers together by doing the following substitution. We can have ec times e3x, because the same base implies that we're going to add the powers together. So what happens to this? Well, this term is always going to be a constant. It's just e to the power of some constant. So that's going to be another constant. So it is very customary to substitute this by a single constant, and we can call it anything. In this case, I'm just going to call it a, such that our final solution, so that's our general solution to this equation, is going to be equals to a e3x. So as I showed you in the previous video, the solution to a differential equation of this kind is actually an exponential function, and that's quite a nice thing to come across. So this is kind of the simplest thing you can come across when it comes to differential equations. Now you might wonder why I'm calling this a general solution. It's because we can have an infinite number of solutions because we can choose any value for the constant a. If we wanted to find a specific solution, so a single solution, we would need an initial condition. And this is something I mentioned in the previous video as well. An initial condition is one that gives us the value of the function y when x equals to 0. So in this case, let's suppose that the initial condition that they give us is 5. So at x equals to 0, the value of y is 5. So what can we do with this? Well, we just need to substitute it for the function that we just derived, and we just need to write y of 0 equals to 5, and that's going to be equal to this side of the equation, so that's going to be a e3, and we're going to substitute x by 0 because that's the input here. So this is going to be 0, and this term is just going to go to 1. So what that means is that a is going to be equal to 5, and finally our general solution, sorry, our particular solution, specific solution to this problem is going to be 5e3x. So that is essentially how you solve this type of equation, and there are many different ways in which you can manipulate these things around, but this is the general case in which you have a separable differential equation. And in the next video, I'm going to show you another example that builds onto this equation, which is actually called the Malthus equation because it was originally used to model population growth. And in the next video, I'm going to show you how to expand this equation to a nonlinear differential equation that also models another type of population growth.